Şuradan kaydı açayım ben bir. Bu sefer de şey gitti ya, canlı diyor. Ha?
Şimdi herhalde kaydediyor.
Hı? Şu muydu?
Şimdi bu record.
Good morning.
Good morning.
Sayın Özcan. Dear participants, first of all, welcome to the International Conference on Advanced Materials Science and Engineering and High-Tech Device Applications. I hope the conference will contribute to the scientific committee and will be successful. With these feelings, I thank all participants for their support on behalf of organization committee. We start with the first presentation. Mr. Özdan.
Thank you very much, dear Chairman and participants. My name is Sertaç Özdan from Ankara Yıldırım Beyazıt University, Faculty of Dentistry at Prosthodontics Department. My study is about the effects of various amount residues, ytria, stabilized zirconia powder addition to polymetal metacrilat matrix composites on microstructural and mechanical properties. The aim of this study was to determine the effect of various amounts of recycled ytria-stabilized zirconia to in turn polymetal metacrilat resin matrix on microstructural and mechanical properties. Metal metacrilat is one of the most preferred prosthodontic material in dentistry for many years by reasons such as low cost, simple application, and easy polishing. Polymetal metacrilat-based provisional restoration is an important step that shouldn't be neglected in the prosthodontic treatment process in order to protect the prepared tooth tissue from heat and food to provide aesthetics function, formation of the gum form, and the occlusion for a certain period of time. However, purely polymetal metacrilat has insufficient mechanical strength and surface hardness. Prolonged use can cause cracking or fracture of temporary restorations, especially in long-span fixed prostheses and areas with heavy occlusal load in the posterior region. When temporary restorations are broken, they can damage oral tissues and even be swallowed by the patients. During the production of CAD/CAM zirconia dental prosthesis, residual zirconia powder is formed, as seen in the picture. Evaluating the unused zirconia powder will have economic benefits. We can see the CAD/CAM process of the zirconia powder from zirconia discs. For this aim, various amount of recycled heat-resistant zirconia added to polymetal metacrilat and cold cured with positive pressure subsequently. Zirconia blocks residue powders were added to acrylic resin monomer and mixed manually with a stainless steel spatula until homogeneously dispersed. After gaining homogeneous appearance, methyl metacrilat liquid was added until achieving homogeneous mixture. At table 1, we can see the powder polymetal metacrilat and liquid methyl metacrilat weights with residue zirconia weight percentage of groups. We added zirconia powder at 10 groups and weight percentage by adding testing at this weight lengths. And at this study, we use scanning electron microscopy, energy dispersive electron spectrophotometry, and Fourier transformation infrared spectrometry was used for microstructural analysis of the specimens. In figure 1, we can see the heat-resistant zirconia particles, SEM figure, and ADS analysis results. According to SEM figures residues, heat-resistant zirconia particle size were between 500 nanometer and 17 micrometer. According to the results, chemical compositions consist of 65.7 ytria weight percent, zirconia weight percent, 28.1 oxygen weight percent, 4.5 yttrium weight percent, and 1.7 hafnium weight percent. It can be clearly seen from the figure 1 that EDS map analysis, all phases have homogeneous distributions of the particles. Figure 2 shows the SEM microstructure and ADS analysis of unreinforced polymetal metacrilat and zirconium oxide reinforced composite fracture structures. Unreinforced polymetal metacrilat fracture surfaces were dense, smooth, and homogeneous at figure A. Also, there were no porosity in unreinforced samples. Figure A shows this. With addition, yttrium zirconia to polymetal metacrilat, fracture surface roughness significantly increased. According to the figure 2A, after 68% yttrium zirconia amount caused yttrium zirconia agglomeration in the matrix. We can see from figure E. And at figure 3 shows the analysis results of unreinforced polymetal metacrilat at 25, 40, 60, 70 addition of reinforced polymetal metacrilat. And 5 new strong absorption peaks were seen at wave numbers, as written here. And we compared the unreinforced polymetal metacrilat. And we used Vickers micro-hardness test as for comparing mechanical properties, and the surface roughness we measured with 2D profilometer. Also, composite stands were measured with Archimedes method. And we can see at figure 4, Vickers hardness and density variation with yttrium zirconia amount. Micro-hardness was increased with increasing amount of powder until 68% addition from 23.45 to 31.18. That means hardness value increased 24%. However, over the 68% addition were decreased because the zirconium oxide agglomeration in the composite structure. And we can see here the density of the samples. Densities were increased with addition of powders because polymetal metacrilat and yttrium zirconia density 1.70 and 5.97 respectively. This shows that density 5.1 times higher than polymetal metacrilat. Also shown in figure 5, the unreinforced polymetal metacrilat and yttrium zirconia reinforced polymetal metacrilat matrix composite low amount addition wasn't significantly affect surface roughness. However, increasing the powder addition, surface roughness increased proportionally. Over 60% surface roughness sharply increased due to the high amount yttrium zirconia agglomerations. And we can see the values and statistical conversions of the power additions. Through the 60%, Vickers hardness, surface roughness was increased, and then the above additions were decreased the values. And we can say that when the increment yttrium zirconia addition to polymetal metacrilat until 68%, micro hardness, surface roughness, and densities increased. Micro hardness values increased from 22 to 40 Vickers hardness. Over the 68% addition caused agglomeration. Therefore, mechanical properties of polymetal metacrilat was decreased with more than 68% additions. The finding of the present study is agreement with the study presented at Ahmed et al., who evaluated the hardness of nanocomposites with different concentrations using Vickers hardness test, they found that hardness values were increased with an increase in the ratio of zirconium oxide to polymethyl methacrylate, with the highest value being 7 weight percentage. And similarly, Zhang et al. Investigated the zirconium nanoparticles and aluminum borate whiskers in polymethyl methacrylate denture bases at the surface hardness at concentrations 1, 2, 3, 4 weight percentage. The results showed an increase in surface roughness with an increase of zirconium oxide and aluminum borate whiskers content, and the optimum hardness were achieved at 3 weight percentage zirconium oxide nanoparticles. And in another study, the same results were found by Argun et al. It was demonstrated that this study provisional polymethyl methacrylate with advanced mechanical properties was created using recycled zirconia without the need of special additional process steps. This is shown as a low cost and easy to prepare method. Thank you for listening my presentation, dear participants and chairman.
Thank you very much for your beautiful presentation. Thank you also for keeping up with the times,
Okay, thank you.
Mr. Erdoğan. I want to go to the next statement. Thank you.
Okay, thank you very much.
Sayın hocam.
Ersin hocam şu anda bekleyen arkadaş da yok.
Var hocam var. Hemen alıyorum şu anda.
Tamam, tamam. Good morning. Good morning Emine. Duyuyor musun Emine?
Evet.
Heh, I want to go to next statement. Yes, now I promise to the dear Yağız to make the presentation.
Thank you. Duyuyorum hocam.
Hı hı.
Hocam paylaşımı
Yes, share screen diye bir şey var
share screen.
altta.
Stop. Share screen. Yes, now I find it. Can you see my ekranı görebiliyor musunuz hocam?
Evet, evet. Yes.
So today I'm going to talk about experimental investigation of diffusion absorption refrigeration system working with iron, alumina oxide and magnesium oxide, spinel alumina, nanoparticles, added ammonia, water, nanofluid. I'm Emine Yağız Gürbüz, Natural and Applied Science Institute, Gazi University, Ankara. Okay. My presentation outline. I will start with introduction part. Hocam bir dakika şunu bir kapatayım. Okay. I will continue with introduction part and then I will explain what are nanofluids and utilizing nanofluids in the DAR system. Aim of this study, description and experimental system and theoretical analysis, test results, conclusions. We will stop the conclusions. So introduction part, the diffusion absorption refrigeration system is one of the oldest methods of producing refrigeration effect. In this system, the compressor is replaced by an absorber and ammonia used as the refrigerant and water is used as the absorbent. So in here, we don't use heat, we don't use mechanical energy. Rather than mechanical energy, we use heat energy. And we can change the conditions of the refrigerants for the operation of refrigeration cycle. So actually this system introduced in 1921-25 by Munters and Planton, and this type of refrigeration also called as three-fluid absorption system. And in here we have water, ammonia, and hydrogen or helium, as I mentioned before. The main purpose of the system is to eliminate the pump so that there is no moving part. It means that the machine becomes noiseless and the maintaining parts so low comparing to compression system. However, the problem with this system, the COP, coefficient of performance of the system is very low in industrial processes. So what are we doing? What are nanofluids? We need to speak. Nanofluids are a fluid containing nanometer-sized particles called nanoparticles. And the nanoparticles used in, actually, these particles are made of metals, oxides, carbides, or carbon nanotypes. Suspended nanoparticles in various base fluids can alter the fluid flow and heat transfer characteristic of the base fluids. And what we can get with the nanofluids give us larger surface area and improves heat transfer capabilities. So we use nanofluids for enhancing the coefficient of performance ratio. In this system, we use nanofluids, as I mentioned, that we have low efficiency and they are not suitable for large cooling capacity. So we use nanofluids for enhancing the efficiency. The major physical reasons that cause heat transfer performance, adding nanosite metallic particles improves thermal conductivity, which is so important for the thermal systems. And suspended metallic nanoparticles increase the surface area. And also, as I mentioned, that they will increase the effective thermal capacity of fluid and increases turbulence intensity. And also, scattering of nanoparticles cause the homogeneous temperature gradient. So there is some works with nanofluids, and also this in absorption processes. There's different different literature review in here, we can say. I only put the 6 of them, but we have numerous other nanofluid systems and literature reviews. For example, Sözan et al., we have there using nanofluid solution, a working fluid in the dark and higher temperatures obtained in all systems. And other literature, Young et al., and they are saying that results show that titanium oxide, titanium oxide, and titanium other and silicium carbonate nanoparticles show fine dispersion stabilities. Also, Wu et al. Done a study, and they say that enhancement with increasing initial ammonia concentration, and so on. Aim of this study, in this study, the ammonia water-based nanofluids, we use iron oxide, alumina spinel, and 1% and 2%, and also magnesium oxide, alumina spinel, 1% and 2%, and we compare them in experimental system, and we obtain some results. Shortly, I would like to give this description of the system. As you see, we have 7 main parts: a generator, bubble pump, a rectifier, a condenser part, and also evaporator, and a gas heat exchanger part. And also we have absorber in here and solution heat exchanger. And before, I would say that there's 3 different working fluids. We have water as an absorbent, ammonia as a refrigerant, and helium as an auxiliary gas. And also we have nanoparticles in the main solution. I mean the ammonia water solution. So in this experimental system, we have 5 different working fluids, which is 1% magnesium oxide alumina spinel, and 2% magnesium oxide alumina spinel, and the other 1% iron oxide alumina spinel, and the other 2% iron oxide alumina spinel. So we have the base fluid, which is a volume of 250 milliliter, consisting of 25% ammonia and 75% water. And as mentioned, we have 1% and 2% nanoparticles. We have the base fluid. Firstly, we tested base fluid, first step of the experiments, and then we demonstrate the affecting of adding particles. Moreover, we have the surface active agent, which is triton X100. What is the surface active agent? Actually, it improves the stability of nanofluid, and with this surface active agent, the nanoparticles can be in the solution. They don't be in the bottom of the solution. So they will reduce the surface tension and improve the stability. Then we have ultrasonic agitation, ultrasonic bath. for three hours for each solutions, and also 5 hours for each solutions. And the helium gas is charged between 14 and 14.5 bar to the system. So I mentioned, I think, these things. And I would like to talk about some system parameters. We have a generator in here, as you see. We have an insulation in here, which is 75 watts, a watt meter. And also during the test, we have taken from one point to the pressure. There is a pressure transmitter, which is condenser inlet. And we have K-type thermocouples with a precision in different points of the system. So, theoretical analysis. So, what we have here, the rich solution enters to the boiler part, and there's a, as you see in figure 5, generator and bubble pump be here. The rich solution absorbs heat from the generator, and ammonia vapor releases from the rich solution. And then ammonia vapor rises through the bubble pump and reaches to the top of the bubble pump. And this means pure ammonia solution turns into the generator. So here we have some equations, equation 1 and equation 3. And then in continuing of the system, we have rectifier part, and in rectifier part we have equation 4 and 5 and 6 as well. So lastly, we have the performance coefficient of performance for the cooling system, and we can measure the cooling of coefficient of performance with this equation. So I would like to give the results in this part. In here specifically, we see that this COP, coefficient of performance of the main system, main ammonia water, 25% ammonia water is lower than the others, and higher coefficient of performance is in how we are seeing in 2% magnesium oxide alumina spinel. And also the 2% iron oxide alumina spinel is also gives a good coefficient of performance. But the main difference, I mean the main increasement, we can say 1% magnesium oxide aluminate spinel and 2% magnesium oxide aluminate spinel. So in here we have a figure 6, and figure 6 we can see 4 different temperatures. The temperature 7 generator inlet temperature, and in here we can say that for minimizing energy consumption at the generator. So we need to note that there is solution coming from the solution heat exchanger to the generator, and there will be a saturated temperature. So as you see, in also we have the other temperatures in here. And for example, in here, the ammonia water solution and nanoparticle, 2% nanoparticle, magnesium oxide, alumina spinel, has the highest temperature. So which means that there's a high temperature, and it helps us in cooling, and also it helps us minimizing energy consumption. So using nanoparticles is a good is a helpful in here in temperature 7, but in temperature 1b there is no difference, not a significant difference in here. And also we have temperature 1c and temperature 2 Especially, I would like to mention this temperature too, because temperature too, there is not stable, as you see. In base fluid, especially, there is a big difference. There is a big, it is not stable. So it needs to be stable for the system. So the other, we have other temperature 3, temperature 4A, temperature 4C, and temperature 5. This temperature 4A and temperature 4C for the cooling process, the evaporator temperatures, and temperature 5 and temperature 3 we have. For example, in temperature 3, we have a big difference, and there is the highest temperature in here, base fluid. But unfortunately, in literature, it says that temperature 3 needs to be, what is condenser outlet temperature, needs to be lower if we want a high performance of coefficient of performance. At temperature 5, we have evaporator output temperatures, and in here it needs to be higher for the higher coefficient of performance. So we want temperature 5 higher, and in here the nanofluids are higher values, we can see. So conclusion, in this work, the use of various nanoparticles with different ratios was investigated experimentally, and it was observed that coefficient of performance values of the DAR system significantly increased by using nanoparticles. And also the use of nanofluid contains 2% nanoparticle exhibited better performance rather than the 1% nanoparticle. In the maximum COP, coefficient of performance values, we get with 44% better performance than the base fluid, which is so good in the DAR systems, because the main COP of the values are so low. So it's so important, and consequently, the utilization of nanofluid in the DAR system enhance in energy saving, and at the same time indicates more stable working condition, we could say. So it is, yes, last of my presentation.
Thank you very much, Emine, for your beautiful presentation. Anyone want to ask questions? I have a question. Where is the dark cooling system used?
Use it in caravans, in hotel rooms, the minimal systems, not big capacities, but the small systems, we use them.
Thank you. If there is no question, we can move on to the other presentation. Thank you, Mr. Gürbüz.
Thank you, Adnan Hocam.
Yes, now I promise to dear sürücü. Mr. Sürücü.
Buyurun hocam.
Bizden değil, kendi sesini.
Hocam sizin sesiniz bize gelmiyor. Mikrofonunuz kapalı.
Yasin Hocam, siz host olduğunuz için bekleyenleri ben alamıyorum. Şey bitince hemen almamız lazım. Sizde şimdi yetki.
Evet hocam. Evet hocam. Ben size vereyim o zaman. Hostluğu.
Yetkiyi nasıl alalım?
Hocam yapayım. Sizi host yapayım ben hemen.
Tamam.
Bir saniye hocam. Atma hocam bir kişi beklemedeydi zaten. Onu da ben kabul ettim şimdi. Hemen listeye bakıyorum hocam.
Welcome, Mr. Gnok.
Hello. Yes. Thank you.
Yes, now I promise to dear Gnok to make the presentation.
Mm-hmm. Yes. And I think it's at 11:30, right?
Hı-hı.
Hocam saat 11:30
Evet.
dedi.
Dear Peter, can you
Yes.
hear me?
Yes.
The conference program was changed. Because of that, you have to present your presentation now, if possible.
Okay. No problem.
Thank you so much. Yeah, okay. Thank you. You can share your presentation.
Okay.
Yeah.
Let me check. I just need 2 seconds.
Okay.
Okay, and I still have 40 minutes, right?
Yes.
Okay, cool. So then I like to share my screen. Can you see it?
Yes.
Yes.
Okay.
Okay, wonderful. So I just
Good
need
luck.
a laser pointer. Okay, do I start right now or do we wait?
You can start.
Okay, wonderful. So thanks for having me in this conference. What I would like to do is I'd like to give you an overview about what we can do if we use light ions for imaging and analytics, so especially helium and neon ions. And actually what I like to do is I like to show you how that works on a helium ion microscope. And to structure my talk a little bit, I'd like to first give you a brief introduction into the technology, show a little bit about imaging with helium ions, how the images look like if we do that. I also like to show then something about nanofabrication with light ions, with helium and neon, what we can do there in comparison to, for example, gallium ions. And finally, I like to show you that we can also do wonderful SIMS nanoanalytics by using light ions, for example, neon ions. Okay. Let me start with a brief introduction of a helium ion microscope. So I think you're all familiar with scanning electron microscopes. Typically, what you do in a scanning electron microscope is you generate an electron beam and raster it over the sample and collect secondary electrons. In the helium ion microscope, we do actually the same, except that we do not use electrons, we use ions. Now, what is special about that? Typically, if you think about electron microscopes, the most important thing, if it comes to resolution, is the source of the of the instrument. And for high resolution in electron microscopes, we typically use field emission sources. They have a very high brightness, and therefore the beam can be focused into a very small spot. For ions, we cannot produce field emission sources because we have a totally different ion generation process. What we're using here is a gas field ionization source, and that works in the following way. We have a very sharp tip, which is atomically sharp at the very end. We apply a voltage to that tip. That means we generate a strong electrostatic field in front of this tip. Then we bleed in our imaging gas, it's helium or neon. And the gas atoms are ionized in the strong electrostatic field in front of this tip, and they form an ion beam. And then the ion beam is just focused, scanned, rested over the sample, and we're generating secondary electrons, and therefore we are generating a raster image very similar to what we do in a scanning electron microscope. So we can use helium or neon as ion beams here with the same tip. The difference is helium is very good for high resolution imaging. Neon is excellent for nanofabrication. Okay, if we look a little bit closer to that tip, so that's actually the special about this type of microscope. The tip consists of a single crystal tungsten tip. And if you have the right orientation, then you can sharpen this tip in a way that you end up with only 3 single atoms at the very apex. And that means if we apply this electrostatic or this voltage here to the tip, then we have the highest field in front of only these 3 atoms. That means only in front of the 3 single atoms, we have ionization conditions for helium atoms. That means we only generate ions in front of these 3 single atoms. And that means we have an extremely sharp tip that only consists of 3 atoms. And to improve that situation, we place an aperture into the beam path. We select actually the brightest of these 3 emitting atoms. And in the end, we only have an emission from 1 single atom, and that is actually the sharpest tip that you can build. And that leads to the fact that we have a brightness which is about an order of magnitude higher compared to what we have in a field emission system for electrons. And that actually results in the fact that we can focus this beam into much smaller spots than an electron beam. The other thing which is beneficial for that is helium ions have a higher mass than electrons. That means the wavelength is shorter, and that means we're not diffraction limited like we are in an electron microscope. And therefore, we can actually focus the beam in smaller spots, definitely clearly below 0.5 nanometers, and we can do excellent high resolution imaging with that. And to add some more capabilities to the instrument, so I told you already we can use helium and neon with this gas field ionization source. And we can also add a standard gallium FIB to the instrument where we can do cross-section and whatever. So then we have a tool which is very similar to a cross-beam, dual-beam instrument where we can use the gallium beam for creating cross-sections, and we can use helium and neon for high-resolution imaging. Okay, how do images look like that we take with this type of system? First of all, they look very similar to an electron microscope image. The reason is simple. We're rastering a beam over the sample. We're collecting secondary electrons, and that generates a raster image. But now if we look a little bit closer to that, we see some differences. Number one, we see an excellent, good lateral resolution. We see a very, very good surface sensitivity. What is also interesting, we have a very large depth of field. That means the sample is in focus on the very top, the sample is in focus at the very bottom. We do not observe any charging effects. And what is also very interesting is we can do high resolution imaging at very long working distances. So in an SEM, you would go to working distances like 2 millimeter, 1 millimeter if you want to go for the highest resolution. In this instrument here, we can afford to go to very long working distances. And that's a consequence of the fact that the ion beam the ions have a higher mass and a shorter wavelength than electrons. Therefore, we're not diffraction limited, and therefore we can use very small apertures, and that actually results in a beam with a very small convergence angle, and that results in this very, very large depth of field. It's about a factor of 10 bigger compared to a field emission SEM. Okay, if we use a little bit higher currents, we can also use the ions for material modification. So we can, for example, generate small ribbons in graphene, for example, down to 5 nanometer thickness. We can create nanopores in 2D materials, which are of single-digit nanometer size. We can do ion beam lithography on photoresist without any proximity effect, with very high resolution. If we're adding a gas injection system, we can also deposit materials, so we can do 3D build of all kind of different structures. And if we're using higher mass ions like neon, for example, we can also do, we can generate secondary ions, and we can do SIMS, secondary ion mass spectroscopy, and do nano analytics on all kind of different materials. Okay, I'd like to focus on the imaging part a little bit in the beginning. If we take images with a helium ion microscope, what we typically see is a very strong surface detail, so you can see very fine structures here on the surface with excellent resolution. What we also see is we have an extremely good depth of field, so that means the sample is in focus on the top, all the way down to the bottom, we are in focus. So we can also see these structures here at the bottom, so it's very, very easy to image something because you focus on some area of your sample and you always stay in focus, which is really nice. And the other thing is that we do not observe any charging artifacts. The reason for not observing charging artifacts is the following. In an electron microscope, we always have the problem that depending on the beam voltage, we can have positive or negative charge on the sample, and that's very difficult sometimes to compensate. So typically what you do is you do either variable pressure imaging or you do low voltage imaging, but you're always around some equilibrium. With ion beams, it's very easy. We only can put positive charge onto the sample, and we can easily compensate that with a electron flood gun. So that means we can image all kind of samples in their native state without coating them, glass, plastics, biological samples, just image them and use the electron flood gun to compensate for the charge. So we can basically image everything without charging artifacts. Okay. I also told you we have a very good surface sensitivity, and I like to show you a little bit the difference. What is the difference between imaging with electrons on the left-hand side and imaging with ions on the right-hand side? If we want to image a sample at high resolution in an electron microscope, what we normally do is we image with secondary electrons. Okay, so what happens is the electron beam hits the sample. On impact, it will generate a secondary electron. That's called the SE1 electron, and that actually carries all the information about the sample, about the beam surface interaction. Then the beam penetrates deeper into the sample, it's scattered around, and it generates backscattered electrons. And some of these electrons, or it generates faster electrons inside the sample. Some of these electrons can reach the surface and they can leave the surface. These are the backscattered electrons, and when they leave the surface, they're also generating a secondary electron. And that means these secondary electrons, the Se2 electrons, they carry all the information about the interaction volume. That means an electron beam always gives an information about surface and volume, so it's always a combined information. And if we want to actually become very surface sensitive, we need to minimize the interaction volume. That means we need to minimize the Se2 contribution. And therefore, we need to go to very low voltages, like 1 kV, 500 volts, 200 volts, whatever, to become surface sensitive with an electron beam. If we look at helium ions that are hitting a sample, what happens is on impact, again, they will generate a secondary electron, the Se1 electron. But what then happens is the following: the ions are much slower, even at 30 keV compared to an electron beam, because they're much heavier. So they cannot transfer their energy to other electrons inside the sample, and they cannot really generate backscattered electrons. That means the only signal that we get is the signal from the impact, and that means we only get an SE1 information, no matter what the beam energy is. We're always extremely surface sensitive. And I'd like to show you a comparison between electron beam imaging and ion beam imaging. If you buy an expensive field emission SEM, the first sample that you would probably put in is gold on carbon, and you would look for the sharpness of these edges. So this is an SEM image, 15 kV, gold on carbon, and I would say this looks brilliant, wonderful resolution, everything fine. Now I can tell you we have some carbon contamination on the surface of these gold grains. If I want to visualize that in an SEM, what I need to do is I need to go to lower voltages. I need to become more surface sensitive. So I can do that. I can go down to 500 volts and I start to see some grainy structure on the surface. But we also notice that the resolution degrades due to chromatic aberrations. If we're imaging exactly the same in the helium ion microscope, we receive this image here. We have razor sharp edges. We can see the surface contamination, the carbon, razor sharp on the gold grains. This is twice the magnification than this image here. And that means in the helium ion microscope, we do not sacrifice resolution for surface sensitivity. So we always have the full resolution at the surface at all times. And this leads to interesting things that we can actually image single sheet graphene. So this is a monoatomic layer of graphene spanned over these gallium nitride poles, and we can nicely see all these wrinkles, the holes. So it's very easy to really observe at high resolution, even extremely thin samples where you would struggle a lot with electron beams. Here it's a piece of cake. We just take an image at 30 kV and we are extremely surface sensitive. We can also very nicely image biological samples. And the reason is we're very surface sensitive. We have a high resolution and we're not sensitive to charging. And what we can see here, these are bacteria which are attacked by phages. And what you can nicely see is how these phages attach to these bacteria. So we have a wonderful surface sensitivity here, and you can nicely see some of the phages are sitting outside here. They're just attaching to the bacteria, and some of the phages are already inserting their genome, like this one or this one here, into the bacteria. And we can very nicely study these surface interactions between the bacteria and the phages. And I think that's quite interesting that we can have a very, very close look to what happens here on the surface at extremely high resolution, so we can see all the fine tactiles here, whatever. This does not only work for biological samples, it works for all kinds of samples. And what is also interesting is that sometimes ion beams are actually less harmful to a sample compared to an electron beam. So, and this is an example for that. So this is a low-K dielectric coating here on a semiconductor device. What you typically want to do in these structures is you want to measure the sidewall here. We want to measure the dimension of this groove and the shape of this line here. What happens very often if you try to do that in an electron microscope, you observe some shrinkage or swelling of these structures under the electron beam. And to avoid the shrinking of these structures, you need to go to very low voltages like 500 volts, 400 volts, or sometimes even below. And the result of that is that we would lose resolution and we don't have an accurate measurement anymore. If we're imaging that with helium ions, what happens is the beam just penetrates very deep into the sample. It does not do a lot of interaction with a sample surface. The other thing is we're imaging with very low currents. So in an electron microscope, you would typically use something like 100 picoamps. In the ion microscope, we use 0.5, 0.1 picoamps to image. That means we're a factor of 1,000 lower in dose. And that means we do not generate any shrinkage of these structures, and that means we have the capability of imaging very delicate samples without modification. And that's quite interesting as it's an ion beam and not an electron beam. Okay, another example just for high resolution, that's a cross-section through a gate structure of a flash memory. And we can nicely see this tunnel barrier. We can see spacer cap layers. We can see the different materials here at very high resolution yeah, and it's extremely easy to take that image. Okay, so that was a little bit about imaging. We can also use the ion beam if we use a little bit higher currents. We can use the ion beam also for nanomachining, and this is actually what you can get if you just mill something into a gold surface with helium ion. So we get, if we don't take care about what we're doing, we get easily structure sizes below 10 nanometers, and we can do nanomachining with helium. We can do the same with neon ions. There we have a little bit bigger structures, so in the range of, let's say, 20 nanometers or smaller. We can nicely do that. And I told you we also have a gallium beam on the system as an option. So that means we can also use gallium ions. There we create structures in the range of, let's say, 100, 200 nanometers, something like that, if we are only writing into the surface. But what is very nice, what you can see here, we have for a certain feature size, we have the dedicated ion. So we can do the rough milling with the gallium, intermediate stuff with neon, and the very fine stuff with helium. And if we compare the helium structure with the gallium structure, then we find we easily gain a factor of 10 in resolution if we want to go to very small structures. And I like to show you a little bit the quality about what we can get with this helium ion microscope if it comes to nanostructuring. So these are bow tie antennas. That's not a very high resolution example. So we have a gap here in the center of about 11 nanometers. But what I would like to bring your attention to is, if you look at the sidewalls, they're perfectly vertical. With a gallium beam, you would typically see some kind of roundness here and some taper angle. With helium and neon, we don't see that. We just have perfect definition of the structures that we have designed in our computer. And I'd like to show you a few more examples. This is a high resolution example. Again, this is a nanoresonator. And what we wanted to have is actually two round shapes with a gap in the center, which should be smaller than 5 nanometers. The whole sample it's basically gold on glass. And what we did is we used the neon beam to do some rough milling here around, and then we used again the helium beam to make the fine cut here. And if we measure the size, then we have a cut which is in the range of 3 nanometers. And I think there's no other technique in the world available that can really do these extremely fine structures. And I also like to show you a comparison to if we use a gallium beam, what is currently state of the art, and if we use a helium beam to create some kind of nanoresonators. So what we wanted to do here is actually to create a cylindrical shape with a gap around it. And the design rule was the gap should be 30 nanometers. The diameter of the whole thing should be 200 nanometers. If we try to do that with a gallium fib, you see that we have a lot of restrictions due to the beam shape, and we have these kind of these taper angles. So the structure is really not what we wanted to have. So we do not have a gap of 30 nanometers. That's clearly bigger, at least on top, and the whole dimension is much bigger than what we wanted to have. And also, if you look at the resonance frequencies here, it's not what we expected. If we do the same with a helium beam, then we have exactly 200 nanometers across, and we have a gap with exactly 30 nanometers, and we have perfectly vertical sidewalls. And what we can do then is we can take that further and we can say, okay, we want to keep the 200 nanometers, but we only want to have a gap of 8 nanometers, and we can still do that with an excellent precision. And if we do measurements on that resonator, we see we have we're exactly there where we want to be, and it's really we can really do physics with that, and we do not generate artifacts like with these broad ion beams like in a gallium FIB. Okay, we can also use that in all kind of matrices, so we can not print out only one structure, we can print out as many as we like. So we can do arrays of these nanoresonators. And again, if you look at the structures, so we have 8 nanometers here. So it's a nice tool to do extreme high resolution, and we can also do that over larger areas. What is also interesting is we can also use that for ion beam lithography and photoresist. That works in the same way like electron beam lithography. But the difference is, as I told you in the beginning, the ion beam does not generate any backscattered electrons. That means we do not observe a proximity effect like we do for electrons. That means for an electron beam, what you would observe is if you have a single line, you have a very thin line. If you have a dense pattern, your line width changes, it becomes thicker due to the fact that we're generating backscattered electrons, and they will do some exposure around the area where the beam hit the sample. For ions, we do not generate any backscattered electrons. That means we do not any exposure outside of the area where the beam has hit the sample. And that means no matter if we do single lines or a dense pattern, the line width does not change. So currently the best that we could achieve is something like 3.5 nanometers. We can also add a gas injection system to these type of instruments, and that enables us to do ion beam deposition like in a standard gallium FIB system. The only difference is we do much smaller size scale here. So we can generate wires that have a distance of 50 nanometers or 20 nanometers. If we do electrical tests and AFM measurements, we can clearly see they're completely separated. We can create reasonable resistivity here. And the good thing is we do not implant any gallium into these wires. As we use noble gases like helium or neon, we have a more pure deposition, and that's especially interesting if we want to deposit insulators, then we do not have any metal ions inside these insulators. And one application would be to go for quantum computing devices. So if we want to create a microwave resonator here, we would need a thin antenna which has a certain dimension, so width of 70 nanometers, thickness below 40 nanometers, and a length in the range of 2 to 10 microns. This can easily be achieved with depositing such materials with a helium beam. So because we can deposit relatively pure materials, we do not implant any heavy metals into them, and they work in a very nicely way. Okay, so what I've shown you until now is that we were able to do very good nanofabrication. We can do extreme high resolution imaging. What is missing until now, or what was missing in my talk until now, is analytical capabilities. So one drawback of using ions is we do not generate X-rays. So a helium ion beam at 30 kV does not generate any X-rays. Therefore, X-ray analysis does not work. But what we can do is we can, for example, use our neon beam, generate secondary ions, and do elemental analysis by doing SIMS. And what we're typically using here as a detector, so as we're using relatively low currents, we need to make sure that we have a detector setup that is constant measuring and that we have a good transfer system or an ion extraction system that transfers all the ions that we generate into the detector. So typically what many people are using for nowadays for FIP systems, we are also doing that is on some instruments is to use a TOF SIMS. A TOF SIMS has the problem that it has a duty cycle. So what we do is we pulse the beam and we do shots in the range of a nanosecond. And then we have a flight time of a microsecond into the detector. And that means we have a duty cycle of 1 to 1000. That means we only measure 1/1000th of the particles that we generate. Therefore, we decided on this instrument to use a magnetic sector field mass spectrometer that measures in a constant mode. It measures all the time. That means we have no duty cycle, and that means the signal that we get is a factor of 1000 higher compared to what we would get with a TOF SIMS. And in addition to that, we have a transfer optics that extracts all the ions that we generate, transfers them into the entrance aperture of the of our magnetic sector field, and then we can do very nice SIMS analysis here. So what can we do with SIMS? That's obvious. We can create spectra. What is very beneficial here, we're very strong at the low C numbers here. So we can, at the very light elements, we can see hydrogen, we can see lithium, we can nicely see boron, and what we also can get is we see the different isotopes. So we can see lithium-6, lithium-7, hydrogen, hydrogen-2, deuterium. That's very nice, and we see all the different isotopes here of the different elements. That's probably an advantage compared to what we would see with EDS. And what is also very exciting is if we check the spatial resolution that we can achieve in an analytical mode, that's extremely high. So what we were using here, that's a standard sample that you can buy from the that's in German Bundesanstalt für Materialforschung. They generated a sample that consists of aluminum, gallium arsenide, and gallium arsenide, and it's a multi-layer sample, and it has line widths with a very defined distance. So we have a lot of double layers, double lines that we can look at. So, for example, we're looking here for the aluminum signal, and what you can see, we can nicely resolve lines 70 nanometers, 57 nanometers, 40 nanometers, 30 nanometers, 17.5 nanometers. With EDS, you would have no chance to separate these lines, and we can detect a single line in the range of 3.5 nanometers. So this is the resolution that we can achieve in the analytical mode in this tool. And I'd like to show you a few applications where that can be used for. So we can use it to analyze solar cells, obviously lithium-ion batteries. So lithium is probably the best element for SIMS because it ionizes very easily. We can do applications in biology here. We can look for cleanliness on biomedical devices. We can do geology. We can look for nanoparticles in cosmetics, for example. So if you look at titanium oxide that you have in sun cream, you like to know where that ends up in your body and stuff like that. We can look at, obviously, at semiconductor devices, and we can very nicely characterize nanoparticles. So we can image them, and we can look at the elemental distribution inside a nanoparticle, which is, I think, quite interesting because with EDS, you have no chance to do that. And I'd like to start with an example looking at a lithium-ion battery. And my example is actually the separator that we want to look at. So the separator sits in between the cathode and the anode, and it's suited to let the lithium ions pass through that and prevents these two, the cathode and anode, from actually connecting to each other to avoid any shorts. If we look at this separator, at an aged separator that has been used before, then we can if we just take an image, we see this separator foil here in the background, and then we see a lot of dirt on that. We see some nanoparticles, we see bigger precipitates, and it would be interesting to see what is all this stuff here. So we can do mass spectrum of the whole thing, and we see a lot of different elements here. And if we do some mapping then, and if we look closer into it, then we can nicely see, first of all, we have the image just with the ion beam. If we only collect the electrons, then we see topography. If we go for the negative spectrum, we can see carbon in the back here of the separator foil. We see oxygen and these nanoparticles, and we see fluorine in these bigger particles here in these precipitates. If we go to the positive spectrum, we can see lithium in red, silicon in green, very nicely. And then we can do some kind of data processing. We can look for different regions of interest, and what we can find out then is that the separator foil is typically carbon. That's obvious. If we look at the precipitates, these is the P, that's typically lithium fluoride. So these are the lithium containing particles, and these small nanoparticles, they are typically silicon oxide. So we can nicely see what's in this sample, and we can characterize this sample in a very nice way at high resolution. Another example would be solar cells, copper, indium, gallium selenide solar cells. If you look at it's typically a stack here of different materials. We can look at that in EDS, also with the SEM. What is interesting about these solar cells is there's a difference in efficiency if they're based on a glass substrate or on an alumina substrate. So glass substrates seem to have a higher efficiency than an alumina substrate. And if we want to investigate why, then we can also do an investigation of this structure here with SIMS. And what we see immediately, if we take a solar cell built on a glass substrate, we see that the potassium of the glass migrates into the grain boundary of the solar cell, and that gives probably a much better efficiency compared to if we have a alumina substrate. We don't see anything in the grain boundary, so nothing migrates into the grain boundaries on the alumina substrate. And just to take that a little bit further, we can do a high resolution SIMS analysis of these grain boundaries, and then we see in green sodium, we see the potassium in red, and we see the gallium in the background here. So now I think this gives a wonderful, it's a wonderful example that we can really do extreme high resolution nanoanalytics in grain boundaries in all kind of structures here. We can obviously use that for analyzing semiconductors with very high resolution, so they have very well-defined structures, and we can reveal structures clearly below 15 nanometers here. And my final example that I'd like to show you is what comes a little bit from biology. Probably you know that titanium oxide is something that we have in our regular food. It's called E171, and it's an ingredient that you have in everything that is white, in toothpaste, sometimes in yogurt, sometimes in low-fat milk. It's used for many things that should appear white, or ice cream, stuff like that. And there are discussions going on if that's healthy or not. And what you can do is actually you can try to feed bacteria with food-grade titanium oxide. And the first thing that you can do then is, if you did that experiment, you can fix your sample, put it into the microscope, and we can take images. So we don't see too much if we only do electron imaging here. But if we use SIMS imaging, then we start to see, so that's the total ion current, so that's not mass filtered. We can see the cells here, the bacteria, and we see some which are intact, and we see some that are not intact anymore. Some are exploded. And then we can look for different masses here. So if we look for the CN signal, then we can nicely see the biology that comes very nice with the CN. It's carbon and nitrogen. That's perfect. The cell membranes are typically chlorine, so we can highlight that too. And we can highlight our titanium oxide nanoparticles if we just go for the titanium signal. And if we put the information together, then we find that cells that have not eaten up any titanium oxide, they're still okay. Cells which have eaten the titanium oxide, they're all exploded. So that's probably a hint that titanium oxide in food is probably not the very best solution. But what I wanted to show here is that we really can analyze nanoparticles also in biological samples. So that brings me to the end of my presentation. And I thank you very much for your attention. And I hope I could bring some information across that imaging and analysis with light ions is very beneficial. Thank you so much.
Thank you very much, Dr. Gunnar, for your beautiful presentation. Anyone want to ask questions? I have a question, Gunnar. Are the photos colored in page 48 for 48?
Page 48.
Yes. Are the photos colored?
This one.
Yes.
Okay, so what we do is we assign a certain color to a certain element. That's what we typically do. So that's the only so the more red, the higher the concentration. Let's put it that way.
Yes.
And then that is what we're typically seeing here. So for SIMS, that's like you would do it with EDS mappings. You just assign a certain color to it.
Thank you very much. Dear participants, if you want, you can send your questions to the authors via email. Yes, now the other presentation. Thank you, Gunnar.
You're welcome. Thank you.
Adnan Hocam merhaba. Sesiniz kısık hocam, mikrofonunuz.
Ersin Hocam merhaba. Bekleyen var mı acaba?
Hocam bekleyen yok şu anda.
Yok.
Videoları belki ona şey yapabilirsiniz hocam.
Videolarda da yok. Onu arkadaş sundu. Videosu olan arkadaş sundu.
Tamam Sayın Hocam. Oturumu kapatabiliriz izninizle.
Tamam. Tekrar bekleyeceğim değil mi? Siz şey yapacaksınız.
Biz kapatıyoruz Sayın Hocam. Siz sunuşunuzu kapatın hocam. Oturumunuzu kapatın.
Diğer arkadaşları bekleyeceğim değil mi? Gelen olursa açacağız.
Kaç kişi vardı hocam salonunuzda?
6 kişi vardı. 3'ü sundu.
Diğerlerinin CD'leri yok değil mi hocam sizde?
Yok. Sunanın bir tanesinin var bizde şeyi.
Hocam
video.
saat 11.30'a kadar beklememiz gerekiyor şu anda. Bekleyelim hocam
Tamam.
isterseniz.
Tamam.
Sayın hocam, Adnan hocam, zaten 11.30'daki sundu sanırım zaten. Sunuşu gerçekleştirildi o 11.30'daki sunum. 11'de bir sunum var.
Evet.
Hocam onu bekleyelim isterseniz biraz.
5-6 dakika bekleyelim. Gecikebilir belki.
Tabii ki hocam. Ben de zaten
Bir
sürekli
de saatler değişmiş. Böyle değildi.
Hı hı.
Onu yazarlar görmemiş olabilir. Bu dün değişmiş saatleri. Bize bir
Öyle
kişi
mi hocam?
eklenince hep kaymış.
Tamam hocam. Tamam hocam.
Tamam.
Biz biraz bekleyelim hocam.
Tamam.
Ben zaten takipteyim sürekli hocam. Gelen birisi olursa hemen katılımını sağlayacağım.
Tamam, teşekkürler. Sağ
Sağ
olun.
olun hocam. Saygılar.